When you look up at the night sky, everything seems pretty peaceful out there, right? Stars twinkling, planets rising and setting, maybe a meteorite or two. But there's actually some really violent stuff that you can't see, like two massive clusters of galaxies, and we're talking clumps of thousands of galaxies smashing into one another. It ain't pretty. Well, actually, it is pretty, but we'll move on from there. Astronomers have watched all that happen, and when it was all over, when the cosmic dust settled, so to speak, left at the scene of the accident was a bunch of dark matter. Dark matter that they say shouldn't be there, at least if our current theories are correct. So how you can explain that one? Mystified by dark matter? Give us a call. 1-800-989-8255 is our number. You can tweet us at SciFri. And here to give us his explanations is Andisheh Mahdavi. He is assistant professor of physics and astronomy at San Francisco State University in California. Welcome to Science Friday, Dr. Mahdavi.
Hello. Thank you so much for having me on the show.
Tell us, what was going on with this collision between the galaxy clusters? Is that a common occurrence?
No, it's not very common. So collisions of this magnitude are pretty rare. We only know of a handful of collisions that are this violent.
And so, Dr. Mahdavi, why is this happening?
Well, so basically in the universe we have, we have matter like us, like you and me. We're made up of atoms, which are made up of protons, neutrons, and electrons, and that's about 15% of the matter that's out there. And over the past 40 years, we've built up pretty solid evidence that actually more like 85% of the total mass of the universe, of the matter in the universe, is this mysterious substance called dark matter. So actually dark matter is everywhere. Up to trillions of dark matter particles are passing through you and me right now without us even ever feeling a thing. But what dark matter does have is gravity. So every galaxy that we see out there, every neighborhood of stars, has this dark matter halo surrounding it. And these things are basically living a happy life together, 85% dark matter, 10% gas, 5% stars. But once in a while, the gravity of these things is so large that they just kind of fall into each other. And this particular cluster that we observed has a collision velocity of 2 million miles an hour. So it results in some pretty spectacular events. But one of the things that shouldn't happen is that dark matter shouldn't be pulled away from the galaxies. We think that galaxies and dark matter grow up together. And even in such a violent collision, they should stay together.
So what you observed is that when they collided together, the dark matter sort of stayed there while the galaxies moved off.
Yeah, and so it wasn't just me. It was a team of colleagues, including Dr. James G. of UC Davis, who is to be really credited for a lot of work on this latest result. And we originally discovered it back in 2007 from the ground using telescopes in Hawaii, and now we've followed it up with space from the Hubble Space Telescope. Yeah. So what we saw when we saw these two clusters collide is that there was some dark matter stripped from the galaxies. Now, it's pretty normal for gas to be stripped from the galaxies, and you might have heard of another cosmic collision called the Bullet Cluster.
Yes.
And so when that's also a couple of clusters of galaxies where they smashed together, and their dark matter wasn't misbehaving. So you couldn't detach the dark matter from the galaxies, and so the gas, of course, was detached, and we understand why that is. It's because gas is charged. Gas has protons and electrons, and so when two clumps of free protons and electrons hit each other, they will slow each other down. But dark matter has no charge. That's why we can't see it, because the only reason you and I could see anything is because there's charges that are being accelerated. That's what light is.
Mm-hmm.
But if something has no charge, it doesn't give off light. So in the Bullet Cluster, dark matter and galaxies stay together just as they should, and in Abell 520, they do not. And that is a mystery as to why exactly that is. There isn't a comfortable explanation that can be readily arrived at.
Is there a theory that what may be happening, or you have to just think about it some more?
Well, so there's a number of things that could be happening. All of them are slightly disturbing. So the first thing is that, well, why did in the bullet cluster dark matter not get left behind, and in this cluster above 520 dark matter did get left behind? Well, one thing that could be happening is that, and this is kind of the explanation we want to avoid the most, because it's really requiring some pretty big rearrangements of our thoughts about our cosmos. So we actually set out to disprove this possibility with the Hubble observation because we were so disturbed by the original 2007 findings. One possibility would be that dark matter has some stickiness to it, and that stickiness depends on how fast you collide things together. So if you collide them really fast, dark matter doesn't stick together, but if you do collide them somewhat slower, there's some stickiness that comes into play, and so it stuck in a Bell 520, and it didn't stick in the bullet cluster because of this velocity-dependent stickiness. Now that's something that would be the kind of final explanation if we could rule out everything else, and of course the big job is ruling out everything else. So in our paper we have a number of possibilities, but again, none of them are easy. None of them are simple. So if you wanted to have ordinary dark matter that has no stickiness, you would have to come up with some very convoluted mechanism for removing this cold dark matter from the galaxies that it loves so much. I mean, it just loves hanging out with these galaxies, doesn't want to let go of them under the cold collisionless dark matter theory, which is our main theory that I think we all accept.
Yeah, but if you stick with the stickiness idea, then you have to give up the other idea, that you think you know what dark matter is.
Yeah, so we actually don't know what dark matter really is. These are all theories. Dark matter is not part of our standard model of physics. The standard model accounts for protons and electrons and neutrons. But one of the things that's really exciting about dark matter, that makes it one of the deepest mysteries of the cosmos, is that we are pretty sure that dark matter is not part of the standard model. So some physics beyond the standard model of physics is involved in the nature of dark matter. And because we're in the dark about physics beyond the standard model, we are in the dark about dark matter. We do not know what even its basic properties are, except the fact that it exists and it has gravitational force to it.
So you're even further in the dark now about dark matter.
No, I think we're getting somewhere here. If we can sort of pull together our simulations here, a lot of simulation work is going to have to be done to really see how unlikely is it to get a freak clump of collisionless dark matter like this one. Maybe there was a dark matter clump that formed out there somewhere in the cosmos by itself, and it was kind of starved of gas, and because it was starved of gas, it didn't make any galaxies really inside it, and so it wound up by chance in the middle of this collision. That kind of freak occurrence, we'd have to quantify the probability of that using simulation. So what's nice about this observation, it gives us a to-do list as far as what we have to check. And if everything we check turns out to be not possible, then we have to turn to this velocity-dependent stickiness idea, and of course, we want to avoid that until we actually confirm that ordinary collisionless dark matter couldn't produce the structure.
Why don't we just catch some dark matter here if it's going through us all the time?
It's very hard. Remember, it has to have some kind of charge to be seen, so we cannot ever see it. It kind of just flows through us, so it really...
sounds like a neutrino or something.
Sounds like a neutrino, right, exactly, except there's a very big difference between the neutrino and the dark matter. Neutrino is part of the standard model. So we understand the neutrino really well, and we know that the neutrino, like right now there is huge numbers of neutrinos also passing to you, which we believe are not the dark matter. These neutrinos we detect because we go to places where it's really dark and really calm, like mines deep underground. And we fill these mines with things like heavy water or chlorine. And once in a while, a neutrino from the sun, neutrinos are byproducts of fusion on the sun. Once in a while, one of these neutrinos will hit a heavy nucleus inside this water, and it will give off a little bit of light. So we have detected neutrinos, and we have modeled them in such a way to convince ourselves that they are not the dark matter. However, there are lab experiments going on looking for possible dark matter annihilation products. Now, what does that mean? That means that, remember, we're in the dark about dark matter. We don't know what the real theory behind it is. But one possibility of the many, many possibilities that are literally, there's dozens of papers published on this every month about what could dark matter be. One of the possibilities is that dark matter decays somehow to some kind of regular standard model particle. And if it does do that, then we may be able to catch those decay products. So, for example, one possibility is we could detect neutrinos that were left over after dark matter annihilated or decayed. And the way we would know those neutrinos are from dark matter and not from the sun is that they'd be coming up from the center of the Earth. So they'd be coming from the wrong direction. And so there's experiments right now underway to try to catch these putative products of dark matter decay in the lab. And thus far, they have not really been successful.
So it's easier to look out into the galaxies and do a
big
experiment that way.
The galaxies really are the thing that told us dark matter had to be there. The clusters of galaxies and the galaxies. And also models of the early Big Bang also tell us so many different lines of evidence over the years. Hard work of so many distinguished people over the past 40 years have really brought us to this.
Well, it looks like you have a lot more interesting work ahead of you now.
Thank you very much.
Thank you, Andisheh Mahdavi, Assistant Professor of Physics and Astronomy at San Francisco State University. Interesting stuff about the dark matter. We have been following it